Good morning. My name is Ho-Jun Lee, and I'm a postdoctoral researcher at CISPA, and I'm very happy to present our work with a nerdy title that discusses portable user privilege separation on x86. This work was done while I was a PhD student at KAIST in conjunction with my former colleague Chi-Hyun Song under supervision of Professor Privcall. So I'm going to begin with the problem statement. So today's applications are increasingly complex, and therefore it is inevitable that they are vulnerable. So the lack of in-process memory isolation is at the heart of the problem. An application secret, for instance, a private key used for securing a communication channel, is just as unprotected as any other arbitrary data within the process. So as we all witnessed in the incident of Heartbleed, one successful exploitation of a bug within a process may be enough for the adversary to extract sensitive data within the process. So we all agree that there is a need for a change at the system level, and there are ongoing efforts and available solutions to the issue. In the recent years, the x86 processor have introduced processor-level security features. Intel SGX, for instance, implements a hardware-level memory protection and provides developers with a new set of primitives for isolating sensitive program components. Processor-level support is fundamental and effective direction towards the mitigation of the problem. Using hypervisors is also a popular approach. Hypervisors serve as a great leverage to isolate and oversee sensitive program memory. However, we argue that developers who target general users may face portability issues adopting these solutions. For instance, SGX is only available on newer Intel processors, and of course, it's not available on AMD processors that are regaining popularity in the recent years. And hypervisor-based solutions require the user machine to be virtualized. So lastly, we have these traditional methods that reuse the process and thread level separation for program isolation. However, the approach requires RPCs that induce significant performance overhead. Also, it is often difficult to achieve a fine-grained isolation using these mechanisms. So we believe that there is a need for a portable and fast mechanism for in-process memory isolation. Our architecture, called LOTR x86, aims to be a portable alternative that developers can incorporate without worrying about compatibility issue or dependency issues. So we believe the possible building blocks for this portable user privilege separation was already there. The x86 architecture in fact has 4 privilege levels. However, only the highest and lowest are used for kernel and user in modern operating systems. LOTR x86 established a more privileged user layer, what we call a PrivUser, by harnessing the underused intermediate rings. You will see that the memory access control scheme in our architecture is privilege-based. This means that the mode switch between the user and PrivUser only changes the privilege of the current context, while the process address space or the page table stay untouched. Also, since we only make use of the existing processor features, our approach is portable across all x86 64 variants. So the concept of PrivUser space that we present can be best understood by drawing an analogy with the kernel and the kernel system call interface. So kernel governs all system resources, and the user applications are forced to make system calls to gain temporary and controlled access to system resources. In LOTR x86, the PrivUser controls application secret, as well as the functions that interact with the secrets. So user program must invoke Privcall to access in-process secrets. So this is what developing a program with LOTR x86 looks like from a developer's perspective. The overall concept and procedures are nearly identical to writing your own system call and using it in your program. The Privcall definition and invocation is intentionally modeled after the Linux kernel's system call interface. To incorporate LOTR x86 into your program, you as developer must write the PrivUser side of the program in parallel to your main program. Secret is to be stored in the PrivUser memory space, and then you can start writing functions that do something useful with the secret. The Privcall define macro that looks just like kernel syscall define is used to declare Privcall functions. Now, in the main program, you should realize that you no longer have direct access to application secret. Operations that require access to secret can only be carried out through invoking Privcall. So when LOTR x86 enabled programs are launched, everything in the PrivUser side is loaded into the protected PrivUser memory space. But having an extra execution mode does not automatically mean that we can readily create a new user privilege layer. We found that the powers of the intermediate rings must be harnessed to be transformed into PrivUser space. So the privilege of each ring is shown in the table. As you can see, the intermediate rings, ring 1 and ring 2 are considered supervisor execution modes, meaning while they do not enjoy the privilege instruction execution right, they can access supervisor memory. As you probably noticed, so there is a problem. So the challenge that our design needs to tackle is this. How do we create a new user privilege layer that sits in between user and kernel with just 4 execution modes and 2 memory access privileges? So the memory space of this new privilege level must be defined by 2 boundaries. We have to make sure that user mode context cannot access PrivUser memory, and at the same time, PrivUser mode must not be able to access kernel memory space. So to create user versus PrivUser memory boundary, LOTR x86 maps PrivUser memory space with supervised pages to prevent user mode access from accessing the secret directly. Again, supervisor pages are accessible in ring 0 through ring 2, but not in the user mode. So when the context enters the PrivUser mode with a Privcall, PrivUser memory becomes accessible. As the PrivUser routine finishes and the control flow returns to the user, this memory becomes inaccessible again. So, okay, it looks like the first memory boundary has been established by using the supervisor pages. However, since the PrivUser mode executes in intermediate rings at its current state, it can access kernel memory without any restrictions. So it's a problem that PrivUser has too much power, and this is against the initial design of our architecture. So we need to find a way to create the second memory boundary. Depending on your age, you probably heard or remember that the x86 architecture used to have an additional memory access mechanism called segmentation. Unfortunately, the feature has been deprecated in the 64-bit mode, but you probably noticed that you can still run 32-bit programs on 64-bit operating systems. This is because the x86 64 actually supports 2 execution modes. The long mode is what we usually refer to as a 64-bit mode, and then there's compatibility mode for 32-bit programs. So one thing that caught our attention was that this 32-bit mode can be used to temporarily revive the forever lost segmentation feature. So our solution for limiting the power of PrivUser mode was to enforce segmentation by making it a 32-bit code segment. 32-bit intermediate code segments are quite unique in that they bear the power of the intermediate rings, but they can be harnessed by enforcing segmentation to limit accessible address range. So this means that we can combine the paging-based access control with segmentation even on 64-bit operating systems. So this is the resulting memory access map in each privilege level in our architecture. So what should be noted here is that the switching of accessible memory regions are privilege-based, meaning there isn't any page table modification or address-based switch in each execution mode switch. So the only thing changes when switching between user and PrivUser is the privilege of the current thread. So it looks like we have established the memory boundaries of the new privilege layer. But another important aspect that defines a privilege layer is its control transfer boundaries. We found that there are some complications and security considerations that must be taken into account. The question is, how do we implement control transfer passage that enable Privcalls and at the same time make this our segmentation enforcement scheme inescapable? So before we discuss the privilege and control transfer of our architecture, I'd like to go through a simplified version of the x86 intersegment control transfer rules. So a long return instruction can be used to jump into the same or less privileged code segments. And then, of course, one does not simply walk into the inner ring without any security checks. So to enter a more privileged ring, you need a call gate that defines a control privilege escalation path. So this call gate is defined by a call gate descriptor in either LDT or GDT. Referencing a call gate with an L call instruction, the context enters a more privileged segment. However, the call gate enforces all calls into the predestined entry point. And when it comes to 32-bit code segments, they are no different than its counterparts. So you can do this. There's no problem setting up a inter-bitness call gate. But however, there's one exception. You cannot have a call gate whose destination segment is 32-bit. We do not have a good explanation for this other than the Intel manual said so. So due to this strange constraint, we see that our Privcall cannot be implemented by a single call gate. But we found that this constraint can be resolved by combining a long call into a call gate and then a long return. So we're saying since we cannot perform a privilege escalating long call into 32-bit mode directly, we simply elevate the privilege first, and then we enter the 32-bit mode to find ourselves in the PrivUser mode. So in summary, we first enter this midway point, what we call a gate mode, then we enter the PrivUser finally. So along with this constraint, the control transfer must satisfy a security guarantee. So we have to carefully consider all possible control transfer passages so that even when the PrivUser control flow is hijacked, there should be no possible uncontrolled transfer that allows PrivUser to escape the segmentation jail and unleash its full power. So given two unused intermediate rings, we have 4 possible ring level assignment for the gain mode and PrivUser mode. But there is only one configuration that works, and this can be illustrated by trying each combination. So let's take a look. So if we place the gain mode at ring 164 and PrivUser at ring 132, attacker can simply prepare a forge stack contents and launch a long return instruction to obtain the full power. So we see that this does not work. So the lesson here is that there should be no 64-bit counterpart in the ring level that is occupied by the PrivUser. Okay, so we see that the combinations 1-1 and 2-2 do not work. So let's check out the next configuration. So in this case, we have gain mode at R2 and PrivUser mode at R1. Again, this configuration does not work. Since gain mode has lower privilege than PrivUser, it can easily escape with the same method. So we learned that the gain mode privilege has to be higher. It should not be lower than PrivUser mode. So by the process of elimination, we see that this must be the only configuration that should work. And yes, this is the only configuration that's possible for our Privcall interface. Let's make sure that there's no possible escape routes to 64-bit full power intermediate rings. PrivUser cannot enter R264 because there is no such segment defined in the tables. It cannot enter gain mode because it's higher privilege than PrivUser mode. And this is also the case for ring 132. There's no call gate nor code segment to jump into. Then you might be thinking, what if it tries to enter kernel mode directly? Well, this particular control transfer is called a system call and is strictly controlled transfer. So we see that there is only possible. This is the only possible configuration that we can establish PrivUser in a secure way. So this is the final control transfer chain of our Privcall. So Privcall is launched from user space, which is a long call into a call gate. It first lands in our gain mode. Our gatekeeper at the gain mode performs a long return into PrivUser, and on the way back, PrivUser enters gain mode again, another through another call gate, and then the game mode again transfers the context back to the initial call site of PrivUser. So we implemented and evaluated a prototype around the concepts we discussed so far. And as you probably noticed in this talk, I focused on the high-level design of our architecture. So I'd like to encourage you to read our paper if you're interested in the implementation details, or if you're simply a Lord of the Rings fan. So we conducted a set of evaluation using the prototype on both Intel and AMD processor to demonstrate portability and feasibility of the approach. So here's the spec of the machines that we used. So we first conducted a microbenchmark that measures the number of cycles consumed by a null Privcall. A Privcall is measured to consume about 1,000 to 1,500 cycles on both PCs. And this is on par with common lightweight C functions such as IOCTL and getTID. The solid bars on the left in the graph are showing single invocation performance, and white bars on the right shows when the functions are called repeatedly in a loop. We also compare the memory protection mechanism of our architecture against the existing memory isolation method. So we created a simple program, and this program is split into sensitive and non-sensitive domain. And sensitive isolation is protected by one of the memory isolation techniques. So in case of LOTR x86, the sensitive domain is placed in the PrivUser. The mmap example represents the approaches that involve page table modification. So to enter the sensitive domain, you have to modify page tables to make them accessible, and then revert the changes when you exit. For the RPC example, we separated the sensitive domain into a different process and implemented invocation of the functions by using remote procedure calls. This particular experiment illustrates the performance advantages of our approach. The privilege-based memory access control of our architecture is proved to be significantly faster than the other two methods that uses either page table modification or RPCs. And to evaluate the feasibility of our approach on real applications, we modified Nginx plus LibreSSL combo to isolate the server private key as well as the functions that access the private key at a high level. So we implemented two Privcalls. The first Privcall loads private key from a file and processes the key into a usable RSA data structure form. Also, another Privcall that signs the data given as argument with the private key. This POC shows how the heartbleed style of attack is mitigated by design. The private key is stored in the PrivUser memory to begin with. The operations that access the private key can only be performed through use of the strictly controlled Privcall interface. And we also evaluated the performance aspect of this POC. So we benchmarked the LOTR x86 enable web server by measuring the server's response time to keep alive requests. So when the client sends a request, the server replies by sending a chunk of a file. And we also varied the size of the file. And so the overhead for the 5K size of a file was measured to be about 35% on Intel and 40% on AMD. But as the size of file increases, the performance overhead induced by Privcalls become relatively negligible, as you can see. So this shows that our architecture can be readily adapted to performance-sensitive applications such as web servers. And so here's a conclusion. LOTR x86 provides portable user privilege separation on x86 by harnessing the underused intermediate rings. Prototype was built to illustrate the design. We also implemented POC top of the prototype with Nginx and LibreSSL to show that this approach is feasible for real applications. So that is all I have today. And thank you very much for your attention. I'll be happy to take any questions. Okay, questions. Please come to the microphone.
Hi, John Criswell, University of Rochester. So nice work. One question I have though is, if I understand correctly, you're comparing against a remote procedure call system, in which you're doing a remote procedure call on a single core system.
Yes.
Right. Okay. So something that's changed in recent years is that we're now in the multi-core era, right? So how do you think your system would compare against a remote procedure call when you can actually have, two thread or two processes running in parallel?
I mean, we haven't done any empirical, experiment in such case, so I can't really tell you how it will be. But there will be an interesting approach that we can compare our architecture to.
Yeah.
So yes.
Yeah. So I think it's, so since things are multi-core now, we have an opportunity that we didn't have, like 10 or 20 years ago. So, okay. Thank you.
Okay. Thank you.
Yep. Carter Yeagerman, Georgia Tech. I missed the first few minutes of your talk, but how would you compare your work to software fault isolation?
So software fault isolation, as far as I know, it has some dependency on control flow defenses, so software fault isolation has to have some kind of CFI in place, if I understand correctly. And also for software fault isolation, you have to instrument all the load and store instructions that may access the secret. But in our case, the secret is already separated in a separate, different protected memory space. And you access the secret using control transfer. So it's two really different approaches.
Would you say that they're worth comparing in the evaluation, or?
So since two approaches are really different, I didn't think it would be possible to directly compare the performance aspect of the two approaches, because you have to for software fault isolation you have to instrument all the instructions, and so it's really not easy to directly compare the performance of two approaches.
Okay, thank you.
Yeah.
One last question. Okay, Leon from Qualcomm. I have a related question with multi-threading. So when you make a call from user mode to the PrivUser mode, do you need to do this copy to user, copy from user kind of thing?
Yes.
Okay.
Correct.
Okay. Thank you very much again.